So the example statement, if you remember, it was the pipe elbow. We had the forces at inlet due to pressure, forces at outlet again due to pressure. We have the reaction force of the elbow due to change of momentum of the fluid. And we had also the weight of the elbow. We had this relationship here. So this one was the conservation of linear momentum in x direction. So we have written it. So, and we have also shown the final form of the energy equation, which is called the Bernoulli's equation. It says that it is steady, no heat transfer, adiabatic system. It is that there is no any work transfer and also frictionless. Okay, with these assumptions, with 4 assumptions, we have got this final relationship, which is called the Bernoulli's equation. And we have said that Bernoulli didn't show the same equation as it is here, but it's named after him. But the Euler has derived the same, exactly the same equation, but the equation is named after Bernoulli. Okay, so this one was the lecture notes from yesterday. So now I'm going to write the known values and as well as to find the forces. Firstly, the pressure at inlet, which is given as 7,000 kilograms per meter squared. Now I will. So yesterday I made a small error with these units here. So I should now convert it into the newtons, and you know that 1 kilogram is 10 newtons. If you work with SI units, so this one is 10 newtons, 1 kilogram. If G is 10 meter per second squared. Okay. And in this case, it is 7,000 kilograms per meter squared, and it means that it is 7,000 times, instead of 1 kilogram, I will write that. So let me write it, kilograms per meter squared, and 1 kilogram is 10 Newton. Okay, and if you cancel out these units, you will have the 70 kilopascal, or 70. Let me write all of the steps here, so there's no problem. 70,000. It is newtons per meter squared, and it is 70 kilopascal. Okay. This one, I had made a small unit error in yesterday, but this is the correct version. There is no problem. Okay, there is no unit error here. So this is 1 kilogram is 10 Newton, and 7,000 kilograms per meter squared. Instead of 1 kilogram, I can write 10 Newtons here, 10 Newton in 1 kilogram. So if the G is 10, and then you will have the 70 kilopascals. The question says that it is 7,000 kilograms per meter squared at inlet. At inlet, we have 70 kilopascals. Okay, so let me see what we have and what we don't know. So firstly, we know the mass flow rate. We have found it yesterday. It was, let me see where it was. We have found it. The mass flow rate, yes, it is here. The mass flow rate is here, which is 300 kilograms per second. It is 300. And the velocity at outlet, we have found it yesterday. It becomes 9.54 meters per second, 9.54. And this one is actually, sorry, this one is velocity at outlet, okay, the velocity itself, but we are looking for x direction velocity at outlet. So what we can do is that I will just draw it again here so that you can see what is the velocity at outlet. So this one was the inlet. Inlet was in x direction, velocity inlet. It is in x direction, there is no problem. But for the outlet, you have some angle here. So this one is the velocity at outlet. And also there is angle, which is the 60 degrees. The angle is between this one and the, so you can see the angle here. So it is between, let me show it here, this one and that one. So this angle here is 60 degrees. This is the velocity at outlet. Okay, angle is shown here. It is 60 degrees. Velocity is 60 degrees, and you have the velocity outlet x component and the velocity outlet y component. Okay. So from here, it will follow that velocity outlet and x direction will be equal to velocity outlet into cosine 60. Okay, so that outlet velocity is 9.54 meters per second. It will be into cosine 60. It will be half, okay. And that one will be equal to With the 4, you will have 7 and 7. Okay, so it will be the velocity in x direction. But you can see it is in negative x direction, so therefore I added the negative sign here. You see that there is a negative sign here due to the direction of it. It will be 4.77. Similarly here, it is 300 kilograms per second for mass flow rate, but velocity at inlet, it is only in x direction. Therefore, there is no need to worry about its components. And at inlet velocity, you have found it yesterday, it was 4.24 meters per second. Okay. And the pressure at inlet, we have found it, it is 70 kilopascal. It is given in the question, it is 7,000 kilograms per meter squared, and it is 700 kilopascal. It will be 7 times 10 to the power of 3. And the area at inlet, it will be just the pi d squared by 4. And the diameter at inlet, which is given as 0.3 here, so 0.3 meters. Okay, so the area at outlet, it is pi d squared by 4 here, and the diameter is at outlet is 0.2 meters, and the pressure at outlet is unknown, we should find it, and Rx is unknown, we should find it, okay? And to find the pressure at outlet, I've said it, we will use the Bernoulli's equation. It says that P by rho plus V squared by 2, V squared by 2 plus GZ is same as at outlet. Okay, this is the Bernoulli's equation. Now I'm going to use the Bernoulli's equation here. So it will be that P by rho plus the V squared by 2 plus the GZ, that is for inlet, should be equal to the same as P by rho plus V squared by 2 plus the GZ, that is for outlet. But in energy equation, there is no need to worry about the components because it is a scalar equation. Since it's a scalar equation, no need for components. But the momentum equations are vector equations, therefore you should write the components. Let's start one by one. For inlet, pressure is 70 kilopascals, and the density is 10 to the power of 3. And the velocity at inlet is 4.24 squared by 2. And the gravity at inlet is, okay, it is the same as at outlet, so gravity is constant, 9.81. And the Z at inlet, now comes that point here. Let me show the picture. So you can see, this one is the inlet. You can see this one is inlet. This one is the outlet. You can see it. If you take the height of Z inlet as 0 meter, if you take it at a 0 meter reference height, then the Z out will be 1.5 meters. Okay. At the end, it doesn't matter if it is. It is very similar to potential energy. It doesn't matter if it is 0 or not. Even if you say that, for example, or Z in is 1 meter, you say it 1 meter, and then the Z out will be 2.5 meters. So the difference in height is important, not the absolute values of the height. You can see the formula here, Z out minus Z in. That is the important stuff, not the Z out absolute value, Z in absolute value. At the end, you will take the difference of it. So therefore, here, if I take the first one as 0 meters, so that the second one will be 9.81 multiplied with 1.5 meters. Okay. The difference in height is important, not the height itself. So it is very same as the potential energy. When we say the potential energy, we are looking for the difference in height, not the height, absolute value of the height. Good. Now that V squared by 2 for outlet, we have found it, it is 9.54. I have said it, energy equation is scalar equation. No need to worry about its components. So 9.54 meters per second. And then from here, you can find the pressure at outlet. So if you have the value, you can tell me the pressure at outlet. This will be the only unknown for this equation. So if you know the pressure at outlet, then we will use the conservation of the linear momentum to find the components of the reaction force Rx, and then we will find the Ry and its moment R. So I'm just waiting for your answer, so to find the value of the pressure at outlet. Okay. So in the meantime, I can show the pressure components again. So the pressure components, you will have the pressure at outlet, it will compress. It is, you see the opposite the velocity pressure, because it always compresses, P out. And this one will also have two components. One will be So if I show it separately here, so this is the P out, and it will have two components. One is the X component, the other one is the Y component. So this one is P out Y, and this one is P out X, and this one is the P out. Again, the angle here is 60 degrees, so therefore the P out X will be equal to P out cosine 60. Okay, so if you have the value for the P out, yes, Ali, so it is 18.8 kilopascals. So for the ease of calculation, I'm making it as 90 kilopascals, but you should know that true value is 18.768. One person says 779. It is not so important. It's a 10 Pascal error. So you can see this is the value, but to make the calculations easier, I make it as 19 kilopascals. Okay, so we have found the pressure at outlet. Now I'm going back to linear momentum equation. It says that the pressure at outlet, but in X direction. We go back to here, pressure at outlet in X direction, it is cosine 60 component. So therefore it will be half of it. So it is pressure at outlet, it will be 9.5. So 9.5 times 10 to the power of 3. Okay. So you see that all of the values are here. You have all of the values, and from this equation, you can find what is the value of Rx. You can tell the value of Rx. You can tell the value of Rx, and then since we found the value of Rx, we will find it. Then I will write the same equation for the y component of the conservation of linear momentum. Then I will find the Ry. And from Rx and the Ry, you can find the value of R, which will be the resultant force. You will take the squares of it, it is hypotenuse. And then the first part of the question will be solved. The next part of the question will be conservation of the angular momentum, and then we will find the line of action of the angular momentum. So what is the value for the Rx? Let's wait for it. Okay. So yes, this part is clear. Okay. Value of Rx. So I've said it, the R value will be equal to Rx squared plus Ry squared. It is just the, okay, remember it is the reaction force by elbow on fluid. Because fluid changes direction. So even if it doesn't change direction, if the magnitude changes, then you will again have the force. Okay. That force is the reaction force of the elbow. Okay. So who has the value for the Rx? This is the for inlet. Let me show the forces here separately. This one is the weight. Now weight will come into picture because if we'll do in y direction momentum balance, so Ry will be here, and also the outlet pressure y direction. It will be in the force balance. Okay. So while you are calculating for the Rx, now let me write the momentum version for the Ry value, that we will have the same. I will draw it again here because you should see the picture. This one is the in outlet, and this one is the inlet. And then the net forces acting on the system, so let me read it. The forces acting on our system here, so the CV in y direction. So we are looking now the y components of it. So that one will be equal to m dot y, m dot v. So it will be that out again in y direction minus m dot v in y direction. So that, yes, we have the value for the Rx. So it is 7958. Yes, I've got all of the same values. So it makes 9 here newtons. Okay, this one is there. So that Ali Mamatari, yes, you are right. So this is the Rx. Now let's write the momentum in y direction. So y direction will be a bit easier because here we have all of the known values. So for the inlet, you can see this one is the velocity inlet, and this is the velocity outlet. So what is the value of the velocity inlet? You can write it as a comment. So what is the value of velocity inlet in y direction? So it is, so what is the value of velocity inlet in y direction? Yes, it is of course 0. Because fluid enters in x direction. You can see it. It enters in x direction. There's no need to find it. So then, now comes the velocity outlet in y direction. So you can see it. So I will write it. I've written it here. So this one is the velocity outlet. It has x component and it has the y component. And therefore, y component will be the sine 60. So it will be that. V out sine 60. And since it is in positive y direction, therefore no need to add the negative sign here. No problem. Now the forces. So we have the pressure at inlet. This one is the pressure at inlet. So the pressure at inlet, it doesn't contribute the forces in y direction. Therefore no need, 0 plus. You have the weight of this, the elbow here. So therefore you will add the weight. So since the weight acts in negative y direction, so therefore you'll add the negative sign here, minus W. For the outlet, you have also the pressure. You can see that pressure outlet is in negative y direction. You can see it is downwards. Therefore, you will have minus P out sine 60. Okay. And also you have the R components here. This one is the R. It is as x component and it has the y component. The y component is it's also in positive direction. Therefore, so it should be positive. It will be equal to, so that m dot that V out sine 60. Okay, just I'm writing the values. Firstly, that P out. So P out, we have calculated that it is 19 kilopascals. It will be 19, 10 to the power of 3. And Ry, it is unknown. And this one was mass flow rate. If you remember, it was 300 kilograms per second. And the velocity at outlet, so where the value, it is 9.54 meters per second. And the weight of the elbow, so if you go back to our problem here, this is the elbow section that we are considering. You can see it. This is the section that we are considering here. And the question says that it has a volume of 0.085 meters cube. This is the volume of it. And so that the weight will be the density into the volume. This here you have only fluid. Okay, this part is only liquid. Okay, it will be that 10 to the power of 3 multiplied with 0.085 meters cube. So you have all of the values, and you can tell me the value of Ry, and we finish. So we finish the value for the Ry. Okay, so if you have the values, you can tell me. You can just write it. And from the value of Ry, so that we can find the value of the R, and then comes the conservation of the angular momentum. With that one, we will finish the example here. So we have said it, R will be equal to Rx squared plus Ry squared. Now let me find the R value now. It will be that Rx squared plus Ry squared. And from here, the Rx value, if so Rx value was equal to, let me write it, 7959. So it is 7959 till the squared plus the Ry value. Now we are going to find it. So then we can find the value of R. Okay. It is 19 kilonewtons, or that Ali 19,018 newtons. Okay, that will be that 19,018 squared, and from here you will get the value of the resultant reaction force. Okay, the value of the resultant reaction force, it will be for the R now. So what is the resultant reaction force here? So you can tell the values. Rajab, yes, the same. The resultant reaction force. Okay, so that if you find it, now the next question will be where it is location. So is it, does it act here, or does it act here, or does it act here? The location of it will be important question for the second part of it. So it makes 20, that Ali says 26.6 newtons. Okay, so we have finished the part here. Okay, so we have finished the resultant reaction force part, and now the question comes what the moment arm of this resultant reaction force is. If you see any error with this calculation with the numerical values, you can tell and I can correct it. So now I'm erasing this part, so I will now write the conservation of angular momentum, because I'm trying to find the moment arm. We are trying to find the moment arm. So now we will use the conservation of angular momentum. It says that the moments acting on the system will be equal to mass flow rate multiplied with the velocity with its arm. So all of R for the outlet minus the mass flow rate with the velocity, again the arm with for inlet. This will be the equation that we are going to write. So that before doing the example, we will make two assumptions here. So the first assumption is that, the first one is that we assume that the pressure inlet, pressure outlet, and the mass flow rate or momentum rate inlet and outlet, okay, act at centroids of areas. That means that the pressure acts here, resultant pressure, the momentum acts here. So in reality, it is a bit different from the centroid, but the distance is so small that you can assume that they are acting at the centroid of the areas. Okay, so this approximation, so there is no second approximation, therefore it is good. So now let's find the moments. You know from the statics or dynamics course that we can take the moments about any point. So any point is okay to take the moments, but the point that you take, if it is not good, if it is not a wise choice, it can increase the number of unknowns. Okay? Very similar to thrust problem. So therefore, I'm going to select the point at the centroid of the inlet area. So I will take the moments about, but you can take any other point. So we'll take the moments about the centroid of inlet area. So let's make this one as A. So we are going to take all of the moments about point A. So therefore, first let me write the forces that we have so that we can see what's going on here. So we have the pressure inlet, so we have the weight, and we have the reaction force, and we have the pressure at outlet. So let me use different color here. We have the pressure at outlet, and yes, all of the forces are here. Now let's write the moments for each force. So for the pressure inlet, so I'm writing the left-hand side now. For the left-hand side, you will have the pressure inlet multiplied with its arm. What is the arm of pressure inlet? You can say the arm of pressure inlet. What is the moment arm of pressure inlet? You can write as a comment. What is the arm of pressure inlet? So we are taking the moments about the centroid of the inlet area. So that it has the pressure inlet. So since this one acts at the centroid of the inlet area, we have said it. So the pressure inlet outlet m dot v and m dot v out, they are acting at the centroid of the inlet area. Therefore, it will have the, yes, as you said, Muhammad Ali, it is 0. It doesn't have any moment arm. So comes the next one, weight. So now the weight, what is the arm of the moment arm of the weight? So sorry, what is the moment arm of weight? You can just say me the value of it from this figure. So from these dimensions here, what is the value of the moment arm for the weight? So then we can consider the clockwise or counterclockwise, but we will take the counterclockwise moments as positive, this one. But for the clockwise moments, so I will take it as negative. So what is the moment arm of the weight? You can see weight acts here, and with respect to point A, I can increase the line of action of the weight, it is not a problem, but with respect to point A, its moment arm is 0.525 meters. Okay. So this one is the weight here, you can see it here. So I'm taking moments about point A. You can see point A here. So that this weight has a moment arm of 0.525 meter, and it rotates in clockwise direction. You can see it is clockwise direction. Therefore, I put a negative sign here. Okay, if you have any problem, you can write it as a comment. So next force is the reaction force R. The reaction force R will have a moment arm. This is actually under question mark, but to see what's going on here, I'm just writing the reaction force. This is point A, and from point A, I will just draw a vertical line to that reaction force R, and this will be the arm of R. Okay, and the R, it seems that it rotates in counterclockwise direction. Therefore, I will write it as positive. This will be R multiplied with arm of R. Okay, this one is unknown. This is the question mark. And then you have pressure at outlet. Okay, we will find the pressure at outlet with its components. And for the outlet pressure, so you will have two components. One will be for X and one will be for the Y component. Let's write it. So this one is the pressure at outlet. It will have the X component and the Y component. This is the X component. So you will have the X component here. And this one is actually Y component, PY. And then you will have also the X component, PX. And we have said that the pressure acts at the centroid. So the PX and the PY are here. Now, firstly, we will find the PX. So let me add it here. PX and its arm. So that PX outlet. So you can see this one is the PX. Just the same PX. And about point A, this is the point A. And this is the PX. It rotates in that direction. and with a moment arm of 1.5 meters. You can see it. This is the px. So it rotates in the clockwise direction with a moment of 1.5 meters with respect to point A. This is the point A. You can see the distance. So it will be negative because it is clockwise. This one is counterclockwise. I should show it. This one is clockwise. It will be multiplied with 1.5. And this one is negative because it is clockwise. So it is counterclockwise, and the next one is the clockwise. Okay, so this one is for px. Okay, now comes the py, and I will ask the py part to you. What do you think the moment arm of py will be? So let me ask this question to you. See your answers. So it will be py outlet y multiplied with its moment arm. So this one is the py, and what do you think the moment arm of py is? So you can actually write the direction of it. Is it clockwise or counterclockwise? So that one person says it is 0.6. So you can see this is the centroid, and if there is no, this part is the distance to that centroid. You can see it. This one is the weight actually. The centroid distance, you can see it is the 0.6 meters, and therefore the py, this one, this is the py here. Py has a moment arm of 0.6 meters, and it rotates in clockwise direction. It is 0.6 meters, and therefore it is negative because it is in clockwise direction. Okay, yes, clockwise, Rajab, clockwise, good. So we have found the left-hand side. You see, I finished the left-hand side. Now comes the right-hand side. For the right-hand side, I will first start with the inlet part. What is the moment arm for the momentum flow rate at inlet? What is the moment arm of it? Can tell it? Yes, it is 0 meters because you can see this one and that one acts at the centroids of the areas. Since it acts at the centroid, this one will not have moment arm, it will be 0. Now comes the outlet part. So to solve the outlet part, I will draw it again here. This is the shape that we are going to consider, and this is the area here, and the velocity will have direction in that way. This is the velocity outlet, and it will have the two components. One is in x direction and the one is in y direction. But now you can see that they act at the same point with the pressure. So this one is same as pressure out, but only the direction is different. The direction is different. For the pressure, it is inwards. Okay, this one is the pressure, but for the velocity, it is the outwards. Therefore, you will have only the direction. So therefore, let me write first that m dot v out first the x direction, and for the x direction, what do you think the moment arm will be? For x direction mass momentum flow rate, what is its moment arm? It is 1.5 meters. Is it clockwise or counterclockwise? Is it clockwise or counterclockwise? Yes, it is counterclockwise. Therefore, it is positive. And mass flow rate, I shouldn't put the negative sign here. I should wait. So that mass flow rate for the outlet, so that it's moment arm, but in y direction. So what is it moment arm in y direction for the mass flow rate? So momentum flow rate, it is 0.6 meters, right? Is it clockwise or counterclockwise? It is again counterclockwise. See, it is positive. So I have finished the momentum equation. I will just write what I've got as a final result and calculate the arm and finish this question. So that you will have the negative W here multiplied with 0.5 to 5 meters. So then plus the R value multiplied with its arm then minus the px at outlet will be multiplied with 1.5 meters, and then py at outlet multiplied with 0.6 meters. That one will be equal to the mass flow rate velocity outlet in x direction multiplied with 1.5 meters plus the mass flow rate and the velocity at outlet in y direction multiplied with 0.6 meters. Okay, these are the values. And for the weight, I will just write the number of it, the numerical values. Numerical value for the weight, it was is x direction and the y direction. Yes, it is 885 actually newtons. The weight is 85 newtons, and the arm is 20. So it is 616 newtons. Px at outlet, so it will be somewhere around here. Px at outlet. So we have found the pressure value. So it was the Bernoulli's equation, which is 19 kilopascals, and outlet will be cosine of it. So it will be 19 10 times the power of 3 and the cosine 60. Similarly, it will be 19 times 10 to the power of 3 and times sine 60. And the mass flow rate for this question is at equal to 300 kilograms per second, and the velocity in x direction, it will be for outlet, it will be 9.54 multiplied with sine 60, sorry, for cosine 60, it will be x direction, cosine 60, and similarly here, it will be 300 multiplied with 954 sine 60. Okay. And from these calculations, you will get the arm of R. So I will not wait for it because I don't have enough time, but you can find the arm of R, and then with this one, you will finish the question. We have finished the question, we have found we will find where it acts. Okay, so this will be the R, and this is the point where we have taken the moments about, and if we extend the line of action of the R, you will have, with respect to point A, you will have this moment R. This one will be the arm of R. Okay. And actually, you can even find the coordinates of it. Okay. So the coordinates, you can find it. This one will be the x1, and this one will be the y. You can find the coordinates of it. Okay, so with this one, we finished the example, and we are moving on to the next example. The example is about the conservation of energy. This one is a very simple example. But if you calculate the value for this one, you can tell me whenever you want. I will just write the value here. For the conservation of energy, we have the steam turbine here. It accepts steam with an enthalpy of 300, so 3,500 kilojoules per kilogram. So here we have the inlet, here you have the outlet. Okay. And the speed of 30 meters per second. Here you have the enthalpy value, which is the 3,500. So this one is inlet, and the velocity at inlet, it is the 30 meters per second. And then the exit of the turbine has saturated mixture with the enthalpy. It is given, okay? There is no need to look at the table. Enthalpy at outlet, which is the 300, so 2300 kilojoules per kilogram. And also the velocity at outlet, which is the 60 meters per second. Okay. Assuming the turbine adiabatic, so this one is adiabatic, and the negligible elevation change, so delta Z is 0, determine the work output. Okay, we should find what is the work output from the turbine, and we will not do that part here. And we will assume that this one is steady. This is the next assumption. This one is steady. Now let's write since we are trying to find the work output, so we should use the conservation of energy. Now let's write the conservation of energy and then simplify it. Conservation of energy says that the internal energy plus the kinetic energy and plus the potential energy change of the turbine. And here I'm selecting the turbine as my CV here. Okay, so the fluid, let's say that not turbine, but fluid inside the turbine. Because here we are interested in more than the turbine itself, fluid. Okay. This one is the change, and that one will be equal to the in minus out. Okay, so I will just write the in minus the out. And for the in quantities, you have the mass flow rate. So mass multiplied with the kinetic energy, sorry, internal energy plus the P by rho plus the kinetic energy plus potential energy. This one is for inlet, and as well as you will have the Q and the work. These are for inlet. Minus, similarly, you will have the mass with the kinetic energy, potential energy, pressure, and as well as you will have the Q and the W. This one is for out. Now, with this question, we will use the approximations given in the question and simplify it. First one, it says that it is steady. Therefore, this one goes to 0. Okay, steady system. Okay, the left-hand side, this part, is only about the system, okay? When we say the steady, means it is a steady system, and the system is this one, okay? And then it says that it is adiabatic. So if it is adiabatic, which term will be 0? You can write it as a comment. If it is adiabatic, which term? So yes, Ali, Sadat, Madat. So the Q is 0. Yes, if it is adiabatic, Q is 0. And it says also negligible elevation change. So it means that when you have the inlet, this one is the inlet, and when you have the outlet, so there is no any height difference, whether it is inlet or outlet. So delta Z is 0. Or you can say Z inlet is same as Z outlet. Therefore, the potential energy changes are neglected. This one is same. Okay, now the question says that there is no mass given in the question. The mass is not given. So what will I do is that I will assume it is per unit mass. So we will do, so everything will be done for per unit mass. Okay. But even you don't do that, you just, so let me write the equation on the next page here. So you will have the mass flow rate, mass multiplied with the U plus the P by rho plus the kinetic energy. Okay. Okay, now we have not done the work part here. So for the turbine, so why do we use the turbine? Turbine produces electricity. It produces electricity. It doesn't matter whether it is a steam turbine. In this case, it is steam, or it can be the water itself, okay, or it can be nuclear. Okay. In any case, the turbine that we have, it produces electricity. Therefore, the work in 0, because it gives you work output out. Okay. Now, if I write the values here, it will be minus m. Similarly here, P by rho plus kinetic energy plus the work. These are in quantities and these are out quantities, and this will be equal to 0. Okay. So if it is 0, then I will write that m u plus P by rho plus the kinetic energy will be equal to m u plus P by rho plus the kinetic energy plus the work out. Okay, so this one is in and that one is out. So now I will cancel out the terms. So this one is the 1, therefore is no any need. Even if it is not 1, you see it cancels out. And the u plus P by rho from thermodynamics, it is the enthalpy, which is u plus P into nu, or it is u plus P by rho. This one is the enthalpy here. This one is the kinetic energy, and similarly, this one is the enthalpy. Now I will write the values. At inlet, you have the 3500 kilojoules per kilogram. So it will be 3500 kilojoules per kilogram. You should convert it into joules by kilogram, SI unit, plus the kinetic energy, which is the V squared by 2. So because this one is M and this one should be V squared by 2. At the end it makes mv squared by 2. Therefore, V squared by 2, you will have the 30 squared by 2. This one is for the inlet. Similarly, for the outlet, the enthalpy value is given. It is 2300 10 to the power of 3 joules by kilogram. This is for the enthalpy. Plus the kinetic energy, it is 60 squared by 2, and plus the work out. And you should remember that the final result will be joules by kilogram. Okay. We can tell the value of work out, and we finish this example. If you have questions, you can ask your question. Madat, Rajab, yes, Q. If you are right, the Q will be 0 for adiabatic systems. If you have questions, you can ask your question in the meantime, but I will wait for the work out from this turbine. Okay. What will be the work output? And you can also notice that the kinetic energy value is very small. You can see kinetic energy on both sides are very small. I can even compare. Okay, so this one makes the 900 divided by the 2. It makes 450. With this one and with that one, you can see it is very, very small. Similarly here, it is 1800 with this one and with that one. You can see the very small value of kinetic energy. So therefore, in thermodynamics, so the enthalpy or the internal energy is more important than the kinetic energy or potential energy. Okay, this enthalpy or internal energy is more important than kinetic energy or the potential energy, and this is called the simple compressible system. Okay, simple compressible system where you have the thermodynamic variables that are more important than the rest of the variables like kinetic energy, potential energy, or magnetic effects, electric effects, etc. So this is called the simple compressible system, and in thermodynamics, so it can be or electric effects, etc. There is a question, can you explain again the turbine part? Yes, for the turbine part, the turbine generates electricity. Okay, therefore, you will have work output. Okay, there is no work input. If you have work input, it means that the turbine uses electricity. Therefore, the work in should be 0. Turbine doesn't use electricity, it gives the electricity. Q is 0 because adiabatic. Potential energy is 0 because it says that the negligible elevation change. Okay, negligible elevation change, the potential energy is 0. Now comes the left-hand side, the change of the properties inside the fluid. So this one is 0 for steady systems. So if you remember, we have given different examples, for example, the map of Azerbaijan or your bank account. So if I summarize it again, if you have the bank account, you have some money here. Okay, some money comes in and some money leaves the system. The money, change of money is 0 with respect to time. If your money inside your bank account doesn't change with respect to time, it is steady. Similarly here, the properties inside the turbine do not change with respect to time. They have fixed internal energy, they have fixed kinetic energy, they have fixed potential energy. Therefore, the left-hand side is 0, or the change of money is 0. But why the change of money is 0? Because inlets and outlets are balanced such that it is 0. For example, your father sends you 5 manats. For example, your grandmother sends you 6 manats, and you spend that money, for example, 3 manats on something, and 7 manats, 8 manats. Okay, on something else, you spend it. Okay, you're spending on food, etc. And you see that the balance inlet and outlet are the same. Your money doesn't change the same amount of money because it is steady. The left-hand side is 0, and in and out balance each other. So yes, this one is enthalpy. H inlet, this one is enthalpy. It is P by rho plus the U. So work out, yes, you have found it, Ali Mohammed Taghe, so that it is, let me write the value, it is 119, 8650 joules by kilogram. You see, it is very large number, very large. So why it is very large number? Because steam, okay? Because steam has very high energy. Therefore, we are using steam for the turbines. If it was water, it couldn't have so large amount of the energy. Okay, with this one, I finished the examples for the conservation laws. Okay, but if I will summarize the equations that we had, and we finish today's lecture. Okay, we had the equation for the conservation of the mass. So, conservation of mass. So it said that the rho velocity and the area is constant, or rho velocity area at inlet is same as rho velocity area at outlet. This one was the conservation of mass. Conservation of the linear momentum, it is a vector equation, and it says that the forces acting on the system will be equal to that the momentum rate, you see the dot here, out minus the momentum rate in. And we had the conservation of the angular momentum, which is R cross mv. So that one will be the moments acting on system will be equal to mass flow rate, again the velocity. You will have its arm. All of these ones are for outlet, minus the mass flow rate and the velocity multiplied with the arm for the inlet. This one was the conservation of the linear angular momentum, and you have the conservation of the energy. And the conservation of the energy, the equation that we used was the delta U plus the delta kinetic energy plus the delta potential energy of the system. Okay, I've given an example what the system means. For example, the bank account map of Azerbaijan. So this one will be equal to mass multiplied with the internal energy, P by rho, plus the kinetic energy, plus the potential energy, plus the Q, and plus the work. Okay, these are the in quantities, minus, similarly here, mass into the U plus P by rho, plus the kinetic energy, plus potential energy, plus the Q, plus the W. These are the out. Okay, so that, but if you can write this equation in this manner too. Okay, it is very easy. So delta U by delta T plus the delta kinetic energy by delta T plus delta potential energy by delta T. We can do that. It is the same equation. Okay, same. You divide each term by this one. Then you will have the mass flow rate m dot into U plus P by rho plus the kinetic energy plus potential energy. Instead of the Q, you will have the Q dot. And instead of the work, you will have the work dot. It will be in minus then m dot, again U plus P by rho plus the kinetic energy and the plus potential energy plus the Q dot and the plus work dot, and this will be out. And for this equation, you have the units as joule, and for this equation, you have the units as watt. That is the thing that you can do for these equations. Okay. And we have said that if it is steady, the left-hand side is 0. So if steady, left-hand side of conservation of energy is 0. And for most of the problems, it is steady. Okay, for most of the problems, it is steady. And then comes the last part, which was the Bernoulli's equation. And the Bernoulli's equation was the specific form of this one. And the specific form was the Bernoulli's equation. And it says that the P by rho plus the V squared by 2 plus GZ is, for inlet, is same as P by rho plus V squared by 2 plus the GZ is outlet. So Bernoulli's equation is special form of it. You can see it says that this term, that term, and this term are constant. Here the kinetic energy, when I say kinetic energy, it is not mv squared by 2, it is v squared by 2. Because there is mass here, it will make mv squared by 2. Similarly here, it is gz. It is v squared by 2, and it is the gz. Okay, this is the 4 conservation laws that we are going to use, and the first one is the scalar equation, this one is scalar, and the second one is the vector. Similarly, this one is also vector, and this one is also scalar equation. Okay, overall it makes 1 here and the 3 here, it makes 4, and the 1 here, it makes 5 equations. So this one, conservation of angular momentum, is not a different equation, it is the special form of the MV. Okay. So we have the 5 equations, so let me write it here. So the 1 equation for conservation of mass, 3 equations for conservation of momentum, and 1 equation from the conservation of energy. So you have 5 equations. Okay. Therefore, you can have only 5 unknowns, okay, maximum. So it means that you can only have maximum of only 5 unknowns for any fluid mechanics problem. Okay. We can have only 5 unknowns for any fluid mechanics problem. That is the essence of the equations. So with this one, I stop the recording here. So I keep it. I will